Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called high power, modeling of electricity market regulations, response of the generating agents. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Electricity system and wholesale market optimization models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. High power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. High power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. Dispatch models are necessary tools to simulate the electricity and gas markets. The Interconnected System Operator, ISO, selects a model for the market simulation, which becomes a guide model for this purpose, since based on this model the market is operated, and other operations that must be carried out in the electricity and gas markets. Many secondary markets move based on this model, in which the ISO, or another market representative, uses the model to establish rights and duties for agents. In some cases, the generating agents can act directly, in others they are simply passive subjects in the market. In any case, the dispatch model is essential for the health of the system and the electricity market, and for the profitability of the agents. The models developed by HI for electricity wholesale systems and markets are dispatch models, economic perfect dispatch, economic regulated dispatch, Cournot-Nash equilibrium dispatch, electricity and gas dispatch, and unit commitment. Complementary models, electricity dispatch and financial analysis, maintenance of regional national grid, electricity supply chain design, and risk management, and energy trading and risk management. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. High power Interconnected Electrical Systems Dispatch Optimization Model. The core model of high power corresponds to the integrated representation of electricity and gas supply chains, which must techno-economically represent the way in which the system is managed. These equations give rise to variations of the model according to the techno-economic concepts that underpin a specific regulation. HI has defined that there are at least four types of similar models to represent the electricity and gas market in the medium term. Economic perfect dispatch, economic regulated dispatch, Nash-Cournot equilibrium dispatch, and unit commitment. Government representatives, the Interconnected System Operator, ISO, and generating agents, all require a dispatch model that supports system planning and scheduling. Traditionally, government representatives and ISO use a model that simulates a market operating in perfect economic conditions, ignoring in many cases the reality of the market, and the generating agents that follow the ISO use the same model. Normally, these models are standardized commercial products, but HI can produce models tailored to each specific case, in short periods. The ED, Electricity Economic Dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. ED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built. Economic perfect dispatch, economic regulated dispatch, Nash-Carnot equilibrium dispatch, and unit commitment. The first 3 models are oriented to planning and the fourth to real-time programming. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. Carnot-Nash equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant power of agents. In competitive markets, hydropower may be lower than in markets dispatched by mathematical models. The effect of the difference on the results of the 2 models is observed below: economic dispatch versus competitive dispatch. The image taken from the lecture Bid-Based Dispatch in Large-Scale Hydroelectric Systems, given by Luis Barroso, presents the production of hydroelectric energy in a competitive market, in which agents take strategic positions. In this case, the hydroelectric power will be lower than in the markets dispatched by mathematical models of traditional economic dispatch. On the other hand, if spot prices are analyzed, the strategic position of generating agents will produce higher spot prices than low-cost dispatch models. Obviously, if an agent uses low-cost dispatch models to estimate their revenue, price by quantity, the financial accounts may not add up. The dominant agents, who exercise the dominant position, will make more money. In this way, the market and the dominated agents will deposit the surplus profit obtained by the dominant agents. This is the main problem faced by the market supervisor. Define a market situation as the exercise of a dominant position. Determine their magnitude, and determine the agents that cause it and that take advantage of it. What is clear is that not all dispatch models produce the same results, and that if the wrong model is used, what should not surprise us is that our decisions are not the best. The results presented by Barroso are consistent with the theoretical support, which is summarized below. The theory of the equilibrium of a perfect market establishes that the equilibrium point is the one that maximizes the social surplus generated by society, which is constituted by the surplus of consumers plus the surplus of producers. The diagram describes the situation. From the mathematical point of view, the equilibrium point is the one that maximizes the integral of the price by the quantity minus the cost of supply. Since economic rationality is assumed, producers will stop producing when the surplus produced reaches zero, defining the solution point of the problem. The reason why market power is exercised is based on the maximization of the profits of the dominant agent, which are generated by transferring part of the surplus of the dominated agent to the surplus of the dominant agent. The bad thing about contracting the amount traded, in this case hydroelectric generation, is the decrease in the social surplus, and therefore in the wealth that the market produces for society. The economic rationality of the dominant agent lies in the fact that its income is a function of the quantity generated and that its maximum, considering the increase in price, is in an amount lower than the ideal for the society. By knowing the behavior of the dominated agent, the dominant agent can determine the price and quantity that is convenient for him to maximize his surplus, to the detriment of society and the dominated agent. The White Paper, Modelos de Máxima Ganancia en el Sector Eléctrico. In English, Maximum Revenue Models in the Electricity Sector, presents the theoretical framework that underpins the MOTSE models. The video, High Power, Autonomous Optimization Software for Electric Sector Enterprises, presents more information about high power. High power. Response of the generating agents. Electricity generating agents, or power companies, respond to the demands of the grid by adjusting their generation mix to meet electricity needs and maximize their profits. They must use sophisticated models to predict future energy needs, incorporating factors such as climate change, fuel costs, and government incentives or costs, and then make investment and/or operating decisions for new plants and technologies. In the long and medium term, They incorporate new electrical power technologies, adapting to market conditions and taking advantage of demand response to balance the grid. In the medium and short term, adapting to the movements of the ISO in the operation of the network. Unfortunately, the use of mathematical models by generating agents is not the general case. Maintenance in the electricity sector. It is common for the dispatch model selected by ISO to be used to determine the optimal maintenance dates for plants in an interconnected system. To do this, it is necessary to adjust the dispatch model including the equations that represent maintenance, and the parameters that represent the feasibility zone of maintenance decisions for each agent. The model used from the point of view of the ISO aims to determine the optimal infrastructure maintenance policies for the electricity and gas sector, minimizing the impact of maintenance on the social surplus or the regional economic benefit. The results to be determined are maintenance dates, or maintenance plan, of the industrial assets in the sector. Ideally, industrial assets are all those that make up the electricity and gas supply chain. Holistic planning is understood as the integrated planning of the major installations of the electricity system. These can be power plants and/or generation units, energy storages, conduction channels, reservoirs and/or dams, transmission lines, transmission system substations, and others. To analyze the above, a model can be generated that integrates the economic dispatch, or any modification of it, with the maintenance model, equations that represent the maintenance processes for each type of installation. The objective of the operation will be to maximize the social surplus, which for electrical systems in which inelastic demand is assumed corresponds to minimizing operating costs. Case: maintenance in the electricity sector, realistic case. Below are the results of an example case for the holistic planning of an electric power generation or transmission system, which can be associated with a region, or a country, or a large private company. The difference between the two processes lies in the fact that the first must be aimed at maximizing the social surplus of the region, while the second seeks to maximize the economic benefits of the operator of the economic assets. This realistic case analyzes the optimization of the generation resources of the Colombian Interconnected System, SIN, from the point of view of maintenance. The case considers the large hydroelectric generation assets, taking the rest of the plants out of the optimization, this only for the purposes of the realistic case. In total, 7 plants are included in the analysis. The diagram shows the unavailability of the generation plants, for maintenance reasons planned by the ISO. The bar in a central implies that it is partially inactive for maintenance. The diagram shows the generation of plants under maintenance. The diagram shows the marginal costs of the system. The model used is a deterministic version of the ISO model, and therefore, as far as possible, the model equalizes marginal costs in time and space. Electricity generating agents, or power companies, respond to the demands of the grid by adjusting their generation mix to meet electricity needs and maximize their profits. The following attitudes can be taken. Reactive: the agent expects and adapts to the ISO actions, and proactive: the agent takes the initiative so that ISO decisions benefit him, respecting the legality of the market. Proactive agents should use sophisticated models to predict the future, or at least use the ISO model intelligently, if they have access to it. High considers that the worst action is reactive. Typically, connectivity between the dispatch model and the maintenance dispatch model is done through parameters that represent the feasibility zone of maintenance decisions for each agent. The feasibility zone of maintenance decisions must be provided by each agent, therefore, these parameters are a variable decision of the agent. The agent's problem will be to determine the value of its parameters, which maximize the revenue to be allocated per the ISO model. These parameters must respect the laws of physics and in many cases the regulation of markets. This is the feasibility zone of the agent's decisions. Response of the generating agents is a multi-game process, in which all agents can participate. Below are several alternatives for proactive agents, which differ in the methodologies and technologies used to address the problem. As is normal, the more realistic the mathematical approach, the greater the economic benefits. Simulating with the ISO model. It is perhaps the simplest approach and is possible to use when the generator has access to the ISO model. Using the ISO model, the central agent can explore the feasibility zone of their parameters and choose the best solution. As mentioned, the problem is a game theory model, so to improve the results, the generating agent can study the behavior of the remaining agents, to find a more robust solution. To do this, the agent has two extreme alternatives. A static model in which each of the optimal parameters of the other agents is studied and, assuming that they make that decision, the central gent determines the optimal value of its parameters. A spatial model, in which the number of other agents is expanded, for example up to 2 agents, and through analysis, the best position of each agent is determined, and with this the value of the parameters of the central agent is determined. Optimizing the parameters of a generator? The most advanced generating agents will take as an alternative, using the same mathematical elements of the ISO model, modify it and convert it into a model to optimize the parameters it must declare. Two types of models can be developed. A stochastic optimization model based on the probabilistic characterization of the possible decisions of the other agents. A stochastic game theory model, in which all agents optimize their decisions. An important aspect of comprehensive modeling is the management and understanding of the target functions. The ISO model's goal, with or without maintenance, is usually to maximize the social surplus, and it does not consider at all how generators' revenues are affected. On the other hand, the objective function of the generator parameter optimization model focuses on maximizing its profits. This is the main algebraic difference between the two models. The following is a summary of the algebraic modeling. The starting point is the selection of a technical economic dispatch model, with physical constraints and an economic objective function. In this case x represents the physical variables, fx the social surplus and gx the physical constraints. Including maintenance parameters in the ISO model is very simple, as the algebraic formulation is not affected. In this case p represents the maintenance parameters, the function kp the parameters effect on the system, and the function rp the parameters effect on the bounds. Converting the ISO model to the generator parameter maintenance model is very simple, as the algebraic formulation is not affected. In this case, the function dp represents the revenue of the generator, or generators, and is the objective function of the new problem. If the source code of the problem is available, converting the problem should be easy. If the model has been developed using Optex, Optimization Expert System, HI's artificial intelligence to implement mathematical models, the conversion is trivial. Real case, availability charge. The data and names have been changed for confidentiality reasons. It corresponds to a case experienced by MW Express, in the assignment of a backup charge to generation plants. The regulation issued by the regulatory office was based on an economic dispatch model, with controlled parameters. The result of the model would be the allocation to backup capacity, which would give each generator annual remuneration rights. The results obtained by studying the actual executions of the dispatch model brought to light problems of inconsistency, which affected MW Express. Given the impossibility of having access to the dispatch model, MW Express hired HI so that, based on the results of the runs carried out, HI would analyze if it was possible to solve the problem. In practice, generators did not have the ability to modify the model, since logic indicated that the highest remuneration was achieved with the highest installed capacity. This is the policy that all generators follow. After studying the dispatch model in depth, HI decided to build an emulator of this model, which was implemented in MS Excel. The emulator was not a dispatch model, it was simply aimed at producing the same results as the model used by ISO. As a control parameter, the installed capacity of the generators was determined. The correct operation of the emulator was valid with many tests. After testing the emulator model in depth, HI uses the model to optimize installed capacity. What is most striking are the cases in which the higher generation produces less backup load. When running runs that varied MW Express's installed capacity, it was detected that the lower the installed capacity, the higher the backup charge and, therefore, the higher the backup revenue. The optimal installed capacity was in the order of 50% of the total generation capacity. To decide, MW Express must make the final calculations, which involve reducing installed capacity would lead to an increase in the backup charge, but revenue from the sale of energy at peaks would decrease. With this information, MW Express made the decision to uninstall capacity. The story showed that it was a wise decision. Auction cases. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.